What if artificial intelligence could read thousands of research papers and synthesize entirely new scientific theories from them? Imagine an AI system that doesn't just propose experiments but actually formulates the compact laws that explain and predict phenomena across disciplines. Let's start by understanding the fundamental challenge this research addresses. Building on this challenge, the authors identify that while AI excels at suggesting experiments, the harder problem is synthesizing theories that aggregate evidence across many studies. They're essentially asking whether AI can do what great scientists like Kepler did, find patterns that unite diverse observations into predictive laws. To make this concrete, the researchers define theories as structured objects with three key components. This format ensures that generated theories aren't just speculation, but are grounded in actual empirical findings with clear boundaries of applicability. Now let's explore how their Theorizer system actually works. The system follows an elegant four-stage process. Starting with a theory query, it first discovers relevant literature, then extracts structured evidence using query-specific schemas, synthesizes theories from this aggregated evidence, and finally refines them through self-reflection. The researchers systematically compare different generation conditions in a 2x2 design. They test whether grounding in literature helps, versus relying purely on parametric knowledge, and whether focusing on accuracy versus novelty produces different theory quality. The scale of this evaluation is truly impressive. These numbers represent an unprecedented scale for automated theory synthesis. The researchers processed over 13,000 papers to generate nearly 3,000 theories, then tested these theories against thousands of additional papers to measure predictive accuracy. Let's examine what they discovered about theory quality. The results clearly show that literature-supported generation produces higher quality theories across multiple dimensions. Importantly, grounding in existing literature doesn't kill creativity. Novelty scores remain comparable while empirical support dramatically improves. Perhaps most convincingly, they developed a backtesting approach where theories generated from older papers are evaluated against newer publications. Literature-supported theories consistently better predict future research findings, with particularly dramatic improvements for novelty-focused generation. The comparison reveals an interesting trade-off between accuracy and novelty objectives. Accuracy-focused theories are more conservative but highly predictive, while novelty-focused theories propose bolder hypotheses that are harder to validate, but potentially more transformative. Let's dive deeper into how the system achieves novelty. The researchers developed a sophisticated framework for measuring novelty across 7 dimensions. This goes beyond simple creativity metrics to capture different ways theories can contribute new scientific insights, from discovering phenomena to unifying existing knowledge. Interestingly, literature grounding doesn't just improve accuracy, it actually enhances the generation process itself. The system avoids repetitive outputs and can synthesize insights across dozens of papers in ways that pure parametric generation cannot achieve. Of course, this approach faces several important limitations. The literature-supported approach comes with significant practical constraints. Beyond the 7-fold cost increase, the system is currently limited to fields with good open access coverage, and many novel predictions remain difficult to validate through existing literature. Let's consider what this research means for the future of scientific discovery. This work opens exciting possibilities for accelerating scientific progress. Imagine AI systems that can continuously scan emerging literature and propose novel theories that human researchers might never discover, simply because they can process far more papers than any individual scientist. The practical applications extend from automated literature reviews to collaborative research tools. Rather than replacing human scientists, this technology could serve as a powerful assistant for theory formation and hypothesis generation across disciplines. The core insights are clear. Literature grounding substantially improves theory quality, structured evaluation makes AI-generated theories accessible, and the scale of analysis reveals patterns that individual researchers would likely miss. However, meaningful trade-offs between accuracy, novelty, and cost remain important considerations. This research demonstrates that AI can indeed synthesize scientific theories at scale by reading vast literature corpora, opening new frontiers for automated scientific discovery. The future may hold AI systems that serve as tireless research assistants, continuously proposing and refining theories as new evidence emerges. To explore more cutting-edge AI research like this, visit emergentmind.com, where artificial intelligence transforms how we understand and generate scientific knowledge.